we've got initiated into basics of Newton's laws. We've learned how to draw basic free body diagrams of particles and collection of particles. Uh, Learned couple of constraints, uh, inextensibility of string, which was referred to as string constraint, and we've learned wedge constraint, which is a constraint pertaining to two bodies, two rigid bodies maintaining contact. Uh, the implication being they maintain the same kinematic status along their common normal, same velocity along their common normal, same acceleration along their common normal, or relative velocity along the common normal being 0, relative acceleration along the common normal being 0. That was the wedge constraint. So not that these are the only kind of constraints that you could encounter. There could be other geometrical constraints in different situations, but these are two most common constraints which deserved special attention, and we've come to terms with these two constraints, I'm assuming. Little bit of our understanding on pulleys and collection of pulleys, fixed, movable, and combination of fixed and movable pulleys. Same with wedges, fixed wedges and movable wedges with particles or bodies sliding down the plane of the wedge. Now, in terms of forces, we have looked at, say, external forces, gravity, we've looked at normal reaction, we have looked at forces in strings, those are tensile forces or tension forces, and we've learnt a little bit about how to hang around with these forces. Yet another force of consequence, which requires an introduction is, when two surfaces, these are two surfaces, say surface 1 and surface 2, and they are in contact. These are two surfaces in contact. And like I mentioned to you, there is a direction which is along the common tangent direction. This is the common tangent to the two surfaces, right? It's called the tangential direction or the parallel direction. It's called the tangential direction or the parallel direction. And there is a direction along which they press each other. This is a direction along which they press each other. And this direction, perpendicular to the common tangent, is called the normal direction. This is the normal direction or the perpendicular direction, right? Now, when two surfaces exert forces on each other, those forces are contact forces. When two surfaces in contact exert forces on each other, those forces are contact forces. And again, they would be subscribing to Newton's third law. They would be commensurate with Newton's third law. They would be equal in magnitude and opposite in direction. The contact forces, again, will have two constituents. One, the contact forces would have a component along the contact forces will have a component along the normal direction or the common normal direction. Those are normal forces. Those are also called normal forces. Say, for example, S2 will exert on S1. S2 will exert on S1 a normal force which is, say, N like this. S2 exerts on S1 a normal force N like this. S1 will exert on S2. S1 will exert on S2 a normal force S like this. These normal forces, like I told you, will always push. S2 would want to push S1 in the normal direction. S1 would want to push S2 in the normal direction. They would always be pushing in character. And Again, these normal forces are self-adjusting forces. These normal forces are self-adjusting forces. They get accommodated based on a requirement, based on a need, they get accommodated, right? I mean, the normal force is a consequence of the kind of motion that S1 and S2 have along their common normal direction. Based on that, the normal force gets determined. It's not that the motion gets determined by the normal force gets determined by the motion. And again, this normal force, in principle, the origin of this normal force is electromagnetic. It's electromagnetic in character. It's a molecular interaction between the two surfaces that results in a normal force. Now, there is another kind of contact force. So normal force is one kind of contact force, which is like a pressing force, which is along the common normal. The other kind of force that they exert on each other is owing to their relative motion along the parallel direction. This is the parallel direction. In this direction, if there is a non-zero relative motion between the two surfaces, then nature wants to prevent relative motion in the parallel direction. So suppose S1 and S2, this is S1, this is S2. Along the parallel direction, S1 has a velocity V1, and along the parallel direction, S2 has a velocity V2. Suppose they have velocities V1 and V2 along the parallel direction or the common tangent direction, right? Now, various possibilities. One, V1 is equal to V2. V1 equal to V2. That means no relative motion along the parallel direction, right? This is a case where there is no relative motion along the parallel direction. Right? And if there is no relative motion along the parallel direction, all's good. There would be no forces that S1 and S2 will exert on each other in the parallel direction. S1 and S2 will then exert no forces on each other in the parallel direction because the two surfaces are moving in harmony with each other in the parallel direction and all's good, right? Therefore, in the parallel direction, there would be no forces that they need to exert on each other. Suppose V1 is different from V2. Say V1 is not equal to V2. Say V1 is not equal to V2. That means there is relative motion in the parallel direction. That means there is a non-zero relative motion in the parallel direction. Relative motion is not zero in the parallel direction. Relative motion is not zero in the parallel direction. Now, nature does not like this. Nature always likes to preserve harmony in the parallel direction. That's the law of nature. Nature would want to prevent this. Nature would want to prevent relative motion in the parallel direction. Suppose V1 is more than V2. Say V1 is more than V2. Say V1 more than V2. Then S1 has a propensity to move faster than S2. S1 would want to move to the right compared to S2. S1 would want to move to the right compared to S2. Yes or no? Right? Then what S2 does to S1 is S2 exerts on S1 a force in this direction. S2 exerts on S1 an opposing force in this direction. In a certain sense, S2 is telling S1, hey dear, don't move that fast. Hold back. I want to move with you. You're moving too fast for me. So S2 will exert on S1 a force in the parallel direction opposing relative motion, trying to or attempting to prevent S2 from parting with S1 in the parallel direction, right? It wants to preserve harmony in the parallel direction. Again, so this is what S2 does to S1, right? It will want to hold back S1, right? Now S1 is not a brute. S1 is also a good fellow, but out of some compulsions, S1 is forced to move faster than S2. But S1 is also a good fellow. He says, I understand that. I do not know how it happened, but let me also facilitate the process of bringing about harmony. So what S1 does to S2 is, all right, brother, I'm also trying to put you in good shape. S2 will exert on S1 an equal and opposite force in the parallel direction, again making a genuine sanguine effort to bring and restore harmony in the parallel direction. So both S1 and S2 are trying to do their bit to bring about harmony in the parallel direction, to bring about harmony in the parallel direction. Both are trying to do their bit, right? Now this is the character of forces in the parallel direction. What is it they are opposed to? They are not opposed to motion. If V1 was to be moving equal to V2, S1 and S2 are friends, buddies like ever, and they say, okay, we don't need to unnecessarily exert forces on each other in the parallel direction. Let's move together as prescribed. But the moment one of them has a velocity higher than the other one, both pitch in. It's not like S1 selfish like human beings. I'm faster, more powerful, and I'll continue to go faster and faster and become more and more powerful. That's the trait of human beings. But inanimate objects have that sense of compassion, right? They say S1, even though S1 is moving faster than S2, it's trying its bit to cause S2 to come to terms with the motion of S1, and again trying to live in peace and harmony, right? This is the character of forces in the parallel direction. This is the character of forces in the parallel direction. So what does it do? It opposes relative motion. It opposes relative motion, right? And again, you know, it doesn't defy Newton's third law. Equal in magnitude and opposite in direction, these parallel forces, right? And these parallel forces that they exert on each other, along the common tangent direction, to bring about zero relative motion, to impose zero relative motion, these forces are called frictional forces. These forces are called frictional forces. Right? Now, the situation that I demonstrated was one where there was actual rubbing along the parallel direction, where there was actual non-zero relative motion along the parallel direction. This case, V1 not equal to V2. And frictional forces that prevail when there is actual relative motion. Frictional forces that prevail when there is actual relative motion. Such frictional forces fall within the category of what's called kinetic friction. They're called kinetic friction. Then this F is written as Fk. This F is written as Fk, kinetic friction. This F is written as Fk, which is kinetic friction. When there is actual rubbing along the parallel direction, when there is non-zero relative motion along the parallel direction, then the frictional forces that prevail between the two contacting surfaces is called kinetic friction, and this F is written as Fk, means kinetic. Fk means F kinetic, right? Now, obviously the objective is plain and simple. The objective is to mitigate, reduce relative motion between the two surfaces. And again, out of experiment, it is found that the relative motion between two surfaces, or rather the kinetic friction between the two surfaces, that enjoy relative motion, they're not enjoying relative motion, but the kinetic friction between two surfaces where there is relative motion in the parallel direction is proportional to the intensity of pressing against each other, how intense they are pressing against each other. That means this Fk is proportional to the normal reaction between the two surfaces. This Fk is proportional to the normal reaction between the two surfaces. It has been found experimentally. it has been found experimentally that the kinetic friction will be proportional to the normal reaction between the two surfaces. The harder the two surfaces press against each other, greater will be the value of Fk. That means more they press against each other, the greater is their bonding, the greater is their desire to maintain harmony. Therefore, greater would be the frictional force that results in attempting to produce harmony. Right? That is what happens. If Fk is proportional to N, kinetic friction proportional to how hard they press against each other, then this Fk can be written as, mathematically written as, a constant times the pressing force between the two surfaces. A constant times the pressing force between the two surfaces. This constant of proportionality will depend on essentially the nature of the two surfaces. It will depend on the nature of the two surfaces. It will be a very weak function of their relative motion. It will be a very weak function of their relative motion. So for normal applications, it's about just the nature of the two surfaces. For a given pair of surfaces, this will be a constant. And this constant is called coefficient of kinetic friction. This is called coefficient of kinetic friction and commonly referred to as mu k. Coefficient of kinetic friction and commonly designated as mu k. So, this kinetic friction between a pair of surfaces, once I have the value of N available to me from other considerations, then this Fk is given by mu k into N. That's the kinetic friction between two surfaces that are enjoying relative motion in the parallel direction. Right? Mu k would be a number that would be given to you, that would be prescribed to you. It is computed out of experiment, right? Now, N would have to be computed from the data of the problem. Say, for example, we have a situation where there are two masses. Say this is mass m1 equal to 10 kgs and there is mass m2 equal to 5 kgs, say. Right? And this, say, is a fixed surface. This is a fixed surface. And say m1 has a velocity v1 equal to 10 meters per second to the right. m2 has a velocity v2 equal to, say, 5 meters per second. Right? So is there relative motion in the parallel direction? This is the parallel direction. Is there relative motion in the parallel direction? Yes. Yes, there is. So m2 is moving slower. m2 is the weaker entity. m1 is the stronger entity. Friction on the two will act in a manner so that it can make the stronger a little weaker and the weaker a little stronger. Right? So m2 will exert a frictional force. So if you're sitting on m2, m1 would seem to be moving to the right because m1 is moving faster. Right? m1 seems to be moving to the right. So m2 will exert on m1 a frictional force in this direction. Yes or no? m2 will exert on m1 a frictional force in this direction. Right? Opposing relative motion. And what would be the nature of friction? Kinetic. Because there is actual relative motion between the two surfaces, because there is actual relative motion between the two surfaces. So this is Fk acting like this. M1 will therefore reciprocate charitably, will exert on M2 an equal and opposite frictional force in this direction, Fk, like this. Yes or no? This is how it happens. Clear? Now, how does one compute Fk? Fk is computed by mu k into normal reaction. Mu k into normal reaction. So, look at M1 and M2. Look at the free body diagram of M1. M1 is 10 kgs. What are the forces acting on M1? There is Mother Earth, 100 newtons downwards, 10 G acting downwards because of Mother Earth, 100 newtons like this. 100 newtons like this. And M2 will exert on M1 a normal reaction R like this. R like this. Right? And suppose they give you the value of mu k between the two surfaces. Suppose mu k is given to be 0.2. Mu k is given to be 0.2, say. Now, one thing, the frictional force, like I said, is like mu k into normal reaction between the two surfaces. Mu k into the normal reaction between the two surfaces. Mu k is known, R would have to be computed. Now, how does one compute R? Look at the equation of motion in the direction of R. In this direction, M1 has no acceleration. So net of all forces in this direction must be 0. So R minus 100 newtons must be 0. Must be 0. So R then turns out to be 100 newtons. R then turns out to be 100 newtons normal reaction between the two surfaces. So the kinetic friction between the two surfaces is obtained as 0.2 into 100 newtons, which is 20 newtons is the kinetic friction between the two surfaces. 20 newtons is the kinetic friction between the two surfaces. Yes or no? Right? And that 20 newtons acts on M1 to the left and on M2 to the right. Right? So, M1 is retarded, M2 is accelerated. So, what's the retardation of M1? The retardation of M1 would be force of friction divided by mass, right? So 20 newtons divided by 10, which is 2 meters per second squared is the retardation of this. Yes or no? Fk is 20 newtons, right? 20 newtons divided by 10 is 2 meters per second squared is the retardation of this. Yes or no? And there is an acceleration of this, A prime. How does one compute the acceleration of this? This Fk divided by mass m. Fk is 20 newtons divided by mass 5, which is 4 meters per second squared is the acceleration of this. 4 meters per second squared is the acceleration of this. Yes or no? Right? Obviously, this acceleration, this retardation is trying to weaken the stronger. This acceleration is trying to weaken the strengthen the weaker. This is the weaker and it is being augmented and accelerated. This is the stronger, it is being retarded and weakened. So that eventually they come at par. Eventually what would happen? The velocity of this will keep decreasing. The velocity of this will keep increasing. Yes or no? Right? Eventually they will reach a common velocity. Eventually at some instant of time they will reach a common velocity. Let's find the common velocity that they reach. So t seconds later, assuming that M2 is large enough so that they don't fall over each other, right? So t seconds later, what is the velocity of mass m1? So v1 is initial velocity 10. I'll use v equal to u plus at. So 10 minus 2 into t is the velocity of this, right? And what about m2? The velocity of m2 would be v2 equal to, m2 is accelerated, velocity would be 5 plus 40, 5 plus 40, v equal to u plus 80, 5 plus 40. Very clearly the velocity of m1 is decreasing, velocity of m2 is increasing. Velocity versus time is a linear graph, yes or no? So how it happens is, for m1, so if I draw in the VT plane velocity time graph, m1 starts with 10 meters per second. m1 starts at t equal to 0 at 10 meters per second, and its velocity is decreasing. Its velocity is decreasing linearly with time, right? What about m2? Velocity is increasing linearly with time. m2, so this is for m1, velocity is decreasing. For m2, which starts with 5 meters per second, its velocity is increasing. That's for m2. V equal to u plus at. The slope of this graph is -2. The slope of this graph is 4. Yes or no? Y equal to mx plus c on comparison. Eventually, do you realize that at some instant of time, t, they will acquire a common velocity? At some instant of time, they will acquire a common velocity, yes or no? At some instant of time, they will acquire a common velocity, right? Now let's see how they, what's their common velocity? V common would be when V1 and V2 are equal, that would be the common velocity. Yes or no? That's how you obtain the common velocity. And let's say at what instant of time their velocities would be the same. So 10 minus 2t equals 5 plus 4t, right? So that gives me 6t equal to 5, or t equal to 5 by 6 of a second. In t equal to 5 by 6 of a second, they acquire a common velocity. So at t equal to 5 by 6, they acquire a common velocity. Now, once they acquire a common velocity, they will not be adamant to follow their respective velocity time graphs. See, what happens is, at t equal, up from t equal to 0 to t equal to 5 by 6, what was the effort being made by each other? Both m1 and m2, they were trying to acquire a common velocity. That was the objective. That's why friction acted. Friction acted because the objective was to acquire a final common velocity. Now, once that velocity is obtained, friction again is not selfish like human beings. It says, my job is done. I'm not going to act beyond this point, right? Right? So eventually they acquire a state where, you know, velocity of 2 is decreasing, velocity of 1 is increasing, and they acquire a common velocity. They acquire a common velocity at t equal to 5 by 6. At t equal to 5 by 6, they acquire a v common. V common is what they acquire. And then both m1 and m2 move with the common velocity ever after. They move with the common velocity ever after. This is how it happens, right? For m1, this is the graph. For m2, this is the graph. It's not like, you know, after they acquire a common velocity, the velocities will keep changing like this. Up to this point, they wanted to come to a common velocity and they had different trajectories of velocity time. But after this, it's not like this will be the velocity time graph different for, then they have a common velocity and they move like this. Because after this point, friction becomes 0. Friction becomes 0. So from t equal to 5 by 6 onwards, kinetic friction ceases to act because there is no need for it to act. Because there is no need for it to act. Yes or no? It will act only to the extent and only to the time where it is required. After which, it will withdraw itself, go into its shell. Right? This is what it does. Now, you know, this was a situation where we had no acceleration of the system in the upward direction, right? But we could have had, say, a situation where say the whole system, in addition to V1 and V2 having velocities in this direction, the whole system was placed in a platform. This was my platform, which was not fixed. This platform was not fixed. This platform was moving up with an acceleration of 10 meters per second square. This platform was moving up with an acceleration of 10 meters per second squared, how does one compute the coefficient of kinetic friction? How does one compute the kinetic friction forces between the two surfaces if this was the case, right? Now, what this upward motion does is, it changes the normal reaction between the two surfaces. It alters the normal reaction between the two surfaces. Say M1 now, look at M1. This is my M1. Forces acting on M1 would be 100 newtons downwards. Normal reaction are upwards. Normal reaction are upwards. Now, realize that for this bottom surface, for M1 and M2, this is their common direction, common normal direction. And for them to maintain contact with each other in this direction, they must have a common acceleration. So if this platform has an acceleration 10 meters per second squared in the common normal direction, M1 must also have an acceleration 10 meters per second squared in the common normal direction. So M1 also has an acceleration 10 meters per second squared in the common normal direction. This belongs to what is commonly referred to as a wedge constraint. This is a wedge constraint having the same kinematic status to maintain contact along the common normal direction, Yes or no? Right? Now, so then the value, so these are the only two forces acting on M1 are the normal reaction that M2 exerts on M1, 100 newtons that Mother Earth does to M1. And the net effect of all of this is that M1 has an acceleration of 10 meters per second squared. Like this. So then, I can write equation of motion of this 10 kg block. What's my equation of motion? R minus 100 equals, this is the cause and this is the effect, right? Equal to M1 into A0. Yes or no? Equal to M1 into A0. M1 is 10 into 10, that makes it 100. So R then, realize, changes. R then is 200 newtons. R then is 200 newtons. But mu k will not change because of this. Mu k is a more innate intrinsic property, right? That only depends on the nature of the two surfaces, which has not changed because of its motion. Motion will not change the fundamental trait of the two surfaces, right? The irregularities that hold the two surfaces together will remain unaltered because of motion or otherwise, right? You know what I'm saying? Okay, so R then becomes 200 newtons. What would be my kinetic friction between the two surfaces? Mu k into n. Mu k into normal reaction. So mu k is given to be 0.2, R is 200, so that makes it 40 newtons. That makes it 40 newtons. So M2 will exert on M1 and Fk equal to 40 newtons like this, and M1 will exert on M2 and equal and opposite 40 newtons in the opposite direction, right? So computation of normal reaction will depend on the situation. Mu k would be a fixed number, right? And therefore kinetic friction will depend on the normal reaction that they exert on each other under various situations. Clear? Now, so this was the case where there was actual relative motion between the two surfaces, and we could compute the kinetic friction that wanted to prevent relative motion. The objective was to prevent relative motion, right? Now there are times that the following might happen. Say, you have a healthy body, okay? But you still go out and say, go to the gym or do some yoga, do some exercises, eat some healthy food. You're fit and fine, but you still do that. Why? Because you want to prevent bad health. You want to prevent bad health. So nature also, instills in us the propensity to take prophylactic action, to take preventive measures, right? So all good, all fine, but there is something that could happen, and to prevent that from happening, we do a certain set of things, right? Now, say there is a mass m1, m equal to 10 kgs, and there is a fixed surface on which it lies. There is a fixed surface on which it lies. Now, suppose this is my parallel direction and this is my normal direction. In the parallel direction, suppose I apply a small value of a small force. I apply a small positive force to the right. Small positive force to the right. Right? Now there is no relative motion between the two surfaces, but there is prospect of relative motion. This small force, no matter how small it is, creates a possibility of relative motion in this direction. This small force creates a prospect of relative motion in the parallel direction, right? So even that possibility instills the desire to prevent relative motion, right? So what it does is, so there is a prospect of m1 moving to the right. There is a prospect of m1 moving to the right as seen by an observer on the fixed surface. So then it takes preventive measures. The fixed surface takes preventive measures. What it does is, it says, all right, I'm going to apply an equal and opposite small force to the left on m1. So this surface exerts on m an equal and opposite small force to the left, preventing relative motion, right? This comes out of interlocking between the two surfaces. It comes out of interlocking between the two surfaces. At the contact area, there are these irregularities which get interlocked, and that interlocking features itself as a force that opposes another force that is trying to prevent relative motion. This is a force that is trying to produce relative motion. This is a force that is trying to prevent relative motion. This is a force trying to produce relative motion. This is a force that is trying to prevent relative motion. And what is the origin of this force? It counts on the interlocking between the two surfaces along their contact surface, right? There is an interlocking because the two surfaces are fundamentally irregular. Under a microscope, if you observe the two surfaces, you would find irregularities that hold on to each other between the two surfaces, right? And it doesn't unnecessarily gets featured only if there is an external force that comes in to produce relative motion. These interlockings then manifest themselves as an opposing force that prevent relative motion. Prospect of relative motion. This produces prospect of relative motion. This prevents relative motion, right? So there is no actual motion between the two surfaces. There is no actual motion between the two surfaces, but there is frictional force which just opposes the externally applied force to prevent relative motion, right? Now, this force F, externally applied force, is balanced by a frictional force, capital F. Say, let me call the frictional force small f, right? Small f will be equal to capital F, which initially is small, right? Now, if this externally applied force increases slightly, right? What happens to the small f? Well, these interlockings still have some capability to prevent relative motion, right? So the frictional force between the two surfaces once again tries to match up with the externally applied force. This frictional force between the two surfaces would try to match up with the increased external force, I increase capital F slightly more, small f will also increase slightly more. Yes or no? And there would be an honest and earnest attempt by friction to exactly counter capital F, although the two surfaces have a capability to produce greater amount of frictional force, let's say, than this, but only that amount of frictional force will be generated that exactly balances the externally applied force and to prevent relative motion between the two surfaces, right? So what really happens is, say, frictional force. This frictional force will depend on the externally applied force. This frictional force will depend on the externally applied force. So this frictional force, if I plot in the y direction, externally applied force along the x direction. So when capital F is 0, frictional force will be 0. There is no need for friction to act at all, right? But when capital F is increased, frictional force just becomes equal to the externally applied force, right? So small f remains equal to capital F up to a certain point of time. Up to a certain point of time, the frictional force, see, this is like y equal to x. This equation is like y equal to x, which is a straight line. So small f versus capital F is like this plotted in the y direction, this plotted in the x direction is like y equal to x, a straight line with slope 1. It's a straight line with slope 1. If it's a straight line with slope 1, that means this angle must be 45 degrees. This angle must be 45 degrees. Yes or no? Small f exactly countering capital F, right? Now, so why has friction acted? Friction has acted in this case to preserve static conditions between the two surfaces. This friction comes into play to maintain static conditions along the parallel direction, to maintain static conditions along the parallel direction. That is a condition of no relative motion. A condition of no relative motion would be referred to as static condition. A condition of no relative motion in the parallel direction will be referred to as static conditions in the parallel direction, right? But, you know, these interlockings, small little fellows, these interlockings that produce small f, in order that capital F could be countered, they keep managing to grow. Small f grows as capital F is growing, right? But eventually, you know, these interlockings will succumb, will give in, will break, will start to dissolve after a while, right? They have a certain strength. After a while, they will dissolve. There is a maximum amount of small f that could be produced between the two surfaces. There is a maximum amount of opposing force small f that could be produced between the two surfaces, right? Which will depend on the extent of interlocking and the strength of the interlocking that the two surfaces have, right? So it's not like small f can have any and every value, right? There is a maximum value that it can have. So small f, which is in this case static friction, small f is static friction between the two surfaces. Small f is static friction. Why is this static friction? Because this friction has enabled static conditions between the two surfaces, has enabled static conditions in the parallel direction. That's why it's called static friction, right? Whenever there is no relative motion between two surfaces, right? Wherever there is only prospect of relative motion between the two surfaces, the frictional force that prevails between the two surfaces is called static friction, right? So static friction is when there is only prospect of relative motion, no actual relative motion between the two surfaces, right? So what really happens is, you know, when this surface rests on this surface, this body rests on this surface, and I apply a value of capital F equal to 0.001 Newton, say for example, then small f if there is static conditions prevalent in the along the common tangent direction, then small f, the frictional force that this surface exerts on small m, will be equal to 0.001 Newton. Yes or no? Right? When capital F becomes 0.005 newtons, say small f also becomes 0.005 newtons. Yes or no? When capital F say becomes 0.01 newtons, small f, let's say, becomes 0.01 newtons. It's trying to keep pace with capital F. It's trying to keep pace with capital F, right? As much as possible, based on these interlockings. Based on the nature of these interlockings, small f would try to keep pace with capital F. Small f will try to keep pace with capital F to preserve static conditions along the common tangent direction. But after a while, say capital F becomes, say for example, 10 newtons. Small f also becomes, say, 10 newtons. It's still preserving. But this, let's say for example, could have been a state where these interlockings are on the verge of seizure. These interlockings are on the verge of seizure. They're about to break. They're about to sinter. Right? Say when small f becomes 10 newtons, there is a great amount of force, interlocking force that prevails here, and this force has a tendency to break. Break these interlockings. These interlockings have a certain strength. They will break beyond a certain force, right? And now, what happens is, when capital F becomes 10.01 Newton, for example, F cannot increase any further. F says, this was my limit. I tried my level best to maintain harmony. Dear capital F, here's my story. I tried to maintain harmony. I tried to match you at all times so that there is no relative motion in the parallel direction. When you were 0.005 Newton, I said, all right, let me also be 0.005 Newton. When you became this, I became this. When you became 0.02 newtons, I also became 0.02 newtons. But, hey dear, this is it. Up to 10 newtons, I could withstand your wrath. After this, I surrender. This is my limit. I can't go beyond this. The maximum value that I can provide to prevent relative motion is 10 newtons, let's say. The frictional force says, like a human being. Unlike a human being. Says, this is it. This is my maximum value. Now you may go on increasing and create relative motion, but I am helpless. This is all that I could do for the sake of everybody's good. But this far and no further. Right? Therefore, this small f, this is one value of static friction, this is another value of static friction. These are all various values of static friction. Static friction assumes values based on externally applied forces, right? When the externally applied force was this, static friction was this. When the externally applied force was this, static friction was this. So static friction has multiple values, unlike kinetic friction. Static friction will depend on the externally applied force, right? Static friction will depend purely on the externally applied force. But static friction has a maximum value. There is a maximum value that static friction can have between two surfaces. There is a maximum value that static friction can have between the two surfaces. This is the maximum value of static friction, let's say, between the two surfaces. That's a maximum value of friction that can exist between two surfaces that have no relative motion between each other, with each other. This is the maximum value of friction that can exist between two surfaces where there is no relative motion at their along the common tangent direction. Right? There is a highest value that static friction can reach. These are all values of static friction, but there is a maximum value of static friction. And this maximum value of static friction, F max, maximum value of static friction is called maximum static friction. Static friction is a variable entity. Unlike kinetic friction, which is a fixed number, static friction is a variable number. Static friction is a variable number because its value will depend on external forces, capital F. But then, irrespective of its variability, there is a constancy about static friction. There is a maximum perceivable value of static friction that can prevail between two surfaces under a given set of conditions. That maximum value of static friction that can prevail under a set of conditions between two surfaces is called maximum static friction. We will commonly designate it as F max stat. F max stat. That's a maximum value of static friction under a given set of conditions between a pair of surfaces. Right? We didn't have to talk of maximum kinetic friction because there was only one value of kinetic friction, but there could have been multiple values of static friction. But there is a limit to the highest value that static friction can attain, and that's called maximum static friction. That's called maximum static friction, right? Again, the law of friction obtained using experiment says that maximum static friction, F max stat, is proportional to the normal reaction between the two surfaces. See, the normal reaction between two surfaces is a variable entity. I can change that. I can press this surface harder against this surface and cause the normal reaction between the two surfaces to grow, right? So, if I double n, then maximum static friction will get doubled. If I half n, then maximum static friction will get halved, right? And for a given n, and for a given, let's say not for a given n, for a given pair of surfaces, this F max stat will be a constant mu s times n, where mu s is a constant of proportionality here, and it's called coefficient of static friction. Like mu k, which depended only on the nature of the two surfaces, mu s will also depend only on the nature of the two surfaces, the kind of irregularities that prevail between the two surfaces. Now, what then happens is, look, like I said, the variation of friction with externally applied force F with F, like I said, static friction will keep matching with externally applied force, but for a certain value of the externally applied force, static friction will reach its highest limit, which is maximum static friction. Once that is reached, these interlockings will start to melt. Relative motion will start. If externally applied force is increased beyond this value F naught, friction can't increase any further. Friction will not increase any further. It has reached its zenith, right? These interlockings will melt. Relative motion commences. Any further increase in capital F will cause relative motion to start. And if relative motion starts, what happens to the frictional value of friction? It becomes kinetic friction. Kinetic friction is given by mu k into n. right? And it has been found using experiment that mu k is less than mu s. Mu k is less than mu s. And if mu k is less than mu s, the new value of kinetic friction, once relative motion starts, then the kinetic friction will become Fk. Fk will be less than Fs max, maximum static friction. Right? So now beyond this point, value of friction will decrease, relative motion starts. Value of friction will decrease a little bit. Value of friction will decrease a little bit. These interlockings have melted, relative motion starts, friction decreases. What's the new character of friction? Kinetic friction. Up to this point, it was static friction. Up to a value of externally applied force F0, it was static friction that prevailed. Further increase in capital F causes relative motion to commence, and the new value of frictional force will be kinetic friction, which will be less than maximum static friction. So kinetic friction, and then after this, once relative motion starts, then no matter how much you increase capital F, the value of frictional force will remain the same. It will remain at a value equal to Fk. It will remain at a value equal to Fk. Kinetic friction will remain at a value equal to Fk. No matter how much you increase capital F, after that, this guy, friction would have resigned to fate. It would have given up. This is how it happens. Yes or no? So you understand the basic premise of static friction, kinetic friction, and how it all goes. Both normal forces and frictional forces fall within the purview of contact forces. While normal forces act along the common normal direction, frictional forces act along the common tangent direction or the parallel direction. Both are electromagnetic in character. Both are fundamentally electromagnetic in character. Frictional force can be categorized in two ways. One, when there is actual relative motion between two surfaces, frictional force that prevails is kinetic, and it would want to oppose relative motion. When there are static conditions prevalent between two surfaces, but there is prospect of relative motion, then friction will oppose that prospect. And that value of frictional force is static friction. It is variable in nature, but it has a maximum limit. And the maximum value of static friction is given by mu s into n. I have deleted that. So is mu s into n is maximum value of static friction, where mu s is the coefficient of static friction. All of you understand this? Yes or no? Not a problem? So what happens is, Suvrat, when I continuously increase capital F, small f also increased. But small f reached its maximum value for an externally applied force, say capital F0, right? Now, after this point, what happens is, when I increase the externally applied force even further, friction can't increase any further, right? Relative motion therefore will start. Once relative motion starts, then these interlockings will melt further, right? And if they melt further, the intensity of friction will decrease. Friction will get reduced in vigor, right? If friction gets friction gets reduced in vigor, and there is relative motion, and the new premise of friction then is kinetic friction, because this is the regime of relative motion, this is the regime of static conditions between the two. Up to this point, static conditions are prevailed. Up to this value of externally applied force, static conditions prevail. And beyond this, kinetic conditions or relative motion starts between the two surfaces. And kinetic friction, so there is dip. There is dip in the value of frictional force when relative motion starts. And the new value of frictional force will be less than maximum static friction. So the new value of frictional force is kinetic friction, which will be less than maximum static friction. This is the whole idea. So after that brief on friction, like I said, kinetic friction is mu k into n, and maximum static friction is like mu s into n. And what I told you was that mu k is slightly less than mu s. Mu k is slightly less than mu s. And therefore, kinetic friction Fk will be slightly less than maximum static friction. Is this what I told you? Right? Kinetic friction will be slightly less than maximum static friction. Now, there are times they would give you the value of mu k and mu s, in which case you would distinguish between kinetic friction and maximum static friction. However, there would be times when, see, like I said, what really happens is there is a slight dip beyond the maximum static friction. Friction slightly dips, F max, S max, right? There is that slight dip, and this is kinetic friction. This length is kinetic friction. Now, this dip generally is very small. From maximum static friction to kinetic friction, the variation is really small sometimes. And when it's really small, and they give you only the value of mu s, they give you only the value of mu s. And if they give you only the value of mu s and kinetic friction also comes into play in a given situation, then it's okay. It's okay to assume that mu s will be approximately equal to mu k. There are times when you have only one of the values given to you, then it's okay to assume that mu s is approximately equal to mu k. That means maximum static friction. It's okay to assume that maximum static friction in such situations is almost the same as kinetic friction. If you don't have mu k separately given to you, but mu s is given to you, you can assume that maximum static friction is almost the same as kinetic friction, right? Now, let me illustrate a little bit. Can I wipe this off? Have you registered all the ideas here? Right. Say there are two blocks, all right. Say this is m1 equal to 20 kgs and say m1 equal to m2 equal to 10 kgs, and there is a fixed smooth horizontal surface. This surface is fixed and smooth. And say between m1 and m2 there is friction. That means along this interface there is friction, and coefficient of static friction, let's say, is given to be 0.1. Coefficient of static friction between m1 and m2 is given to be 0.1. Right? Now, I apply a force on m1 parallel to the horizontal. I apply a horizontal force on m1. I apply a horizontal force on m1. Okay. Now, when this force is really small, there would be no relative motion between m1 and m2. When this force is really small, there would be no relative motion between m1 and m2. They would move together to the right with a common acceleration. But first of all, let me compute some basic properties. Between m1 and m2, if you look at the free body diagram of m1, what's the free body diagram of m1? For m1, there is 200 newtons acting downwards, Mother Earth, and there is normal reaction that m2 will exert on m1 in the upward direction, right? And there is no acceleration of m1 in the upward direction, so R must exactly balance 200 newtons. So R, we know, is 200 newtons between the two surfaces if there is no acceleration in the vertical direction. Now, What is the maximum value of static friction between the two surfaces? F max stat between the two surfaces. That's going to be given by mu s into normal reaction. That's a maximum possible value of static friction, right? Not that all of it will necessarily get used. Only the part that is required will get used, right? But maximum static friction between the two surfaces would be 0.1 into 200, which is 20 newtons. Is the maximum value of static friction between the two surfaces is 20 newtons. Clear? Now, so M2 and M1 will exert frictional forces on each other in the common tangent direction. This is the common tangent direction, right? Would you then want to realize that M1 has a tendency to move to the right compared to M2? Right? If you were sitting on M2, you would find that M1 has a tendency to move to the right on M1 because of this capital F, right? Yes or no? So M2 will exert on M1 a frictional force in this direction. M2 will exert on M1 a frictional force in this direction. M1 will exert on M2 a frictional force in this direction. M1 will exert on M2 a frictional force in this direction. If there is no relative motion between the two, this frictional force will be static. If there is relative motion between the two, this frictional force will be kinetic, right? Now for small values of capital M, there would be no relative motion between the two, and small f would be static in character. Small f would be capital in character. But if I go on increasing capital F, the need to have larger and larger values of small f will go up, right? Right? But it cannot go up forever. Static friction will have an upper limit in this case. What's the maximum possible value of small f in this case? 20 newtons is 20 newtons, right? Let us find what value of capital F will cause this 20 newtons to prevail, to come into place, right? For what value of capital F will relative motion start between the two surfaces? For small values of capital F. So one thing for sure, what drives, if you look at the free body diagram of the lower block, which is M2, what are the forces acting on M2? There is 100 newtons Mother Earth, right? There is normal reaction R1 from the ground on which it is resting, and M1 will exert on M2 a frictional force small f to the right. Yes or no? So then, if M2 is moving with a common acceleration as M1, what is driving M2? Friction. M2 is being driven by friction alone. M2 is being driven by friction alone. Yes or no? So then, what's the maximum possible acceleration of M2? Since M2 is being driven by friction alone, right? So what accelerates M2? Small f. When will M2 reach its maximum acceleration? When small f becomes maximum? Yes or no? M2 will reach its maximum possible acceleration when small f becomes its maximum possible value, maximum static friction. Even though this force F could be 200 into 10 to the power 10 million newtons, right? That will go on adding more and more acceleration to M1, But alas, that's not going to be the same for M2, because the greatest value that M1 can exert on M2 is F max stat, which is 20 newtons, yes or no? So then this limits the acceleration of the upper block is not limited, but the acceleration of the lower block is limited. Why? Because the lower block is driven by friction alone. The lower block doesn't even know of capital F. M1 keeps capital F a closely guarded secret. It doesn't reveal the value of capital F to M2. What it communicates to M2 is only small f. What it communicates to M2 is only small f, the frictional force. Yes or no? Right? So, M2, the lower block, is driven by friction alone. It's oblivious of the magnitude of capital F that is acting on M1. Right? So, M2 driven by friction alone, the maximum possible acceleration that it can have, max acceleration that M2 can have, would be F max stat divided by M2. Yes or no? That's the maximum possible acceleration of the lower block? Yes or no? Huh? And how much is that? Maximum static friction is 20 newtons. So 20 divided by 10, which is 2 meters per second squared. Is the maximum possible acceleration of the lower block. Is there a maximum possible acceleration of the upper block? No, because I go on increasing the value of capital F, and the acceleration of small m1 can go on increasing, right? Because after a while, small f will become, let's say, a maximum of 20 newtons, but capital F can be any value. So there is no limit on the acceleration of the upper block. The greater the value of capital F, I can produce greater accelerations on M1. So there is no limit on the acceleration of this. The maximum possible acceleration of this is 2 meters per second squared. And when does this value of acceleration, when is this value of acceleration reached by M2? When F becomes maximum static. And when F becomes maximum static, M1 and M2 are on the verge of sliding over each other. They are on the verge of sliding over each other. When friction becomes its maximum static value, then there is, M1 is just about on the verge of sliding over M2. M1 is just on the verge of sliding over M2. When frictional force becomes its maximum static value. When frictional force becomes its maximum static value. Yes or no? Right now? So, the moment the acceleration of this becomes the maximum it could be, friction becomes the maximum it could be, and the two blocks are on the verge of sliding over each other at a time when the lower block reaches its maximum acceleration. At a time when the lower block reaches its maximum acceleration. ठीक है ना? All's good ना? Now, what is the maximum common acceleration of the two blocks therefore? The maximum, there is no limit on the acceleration of this. It can have any value of acceleration. But what's the maximum acceleration of the lower block? 2 meters per second squared. When does it happen? It happens at a time when the force of friction between the two becomes its maximum possible. Right? So what's the maximum common acceleration of the two blocks? 2 meters per second squared is the maximum common acceleration. Yes or no? Right now? So, maximum common acceleration of the two blocks is 2 meters per second squared. And when does it happen? It happens when frictional force between the two becomes equal to maximum static friction equal to, in this case, 20 newtons. In this case, 20 newtons. Yes or no? Right? That's the maximum common acceleration of the two blocks. Right? Now, if the acceleration of the lower block is less than 2 meters per second squared, then the frictional force on the lower block will be less than maximum static friction. Yes or no? Right? So, maximum common acceleration is 2 meters per second squared. Now, if the acceleration of the lower block is less than 2 meters per second squared, if the acceleration of the lower block is less than 2 meters per second squared, very clearly, this F has to be less than 20 newtons. This F has to be less than maximum static friction. F has to be, frictional force between the two would have to be less than 20 newtons, which is maximum static friction. Yes or no? And if the friction between the two surfaces is less than maximum static conditions, that means there is no relative motion between the two bodies. If the frictional force between the two bodies is less than maximum static friction, that means there is no relative motion between the two surfaces. That means there is no relative motion between the two surfaces, because the frictional force is static in character. The moment you know that frictional force is less than maximum static, there is no relative motion. There is no relative motion between the two surfaces. That means if there is no relative motion between the two surfaces, means they have a common acceleration. That means they have a common acceleration. Two surfaces have a common acceleration. Right? So, 1. If the maximum acceleration of m2 is 2 meters per second squared. And when does it happen? When F becomes its maximum value equal to 20 newtons. If the acceleration of this at a certain instant of time is found to be 1.5 meters per second squared, then frictional force will be less than 20 newtons. Right? And if the frictional force is less than 20 newtons, that means between the two surfaces static friction prevails. If between the two surfaces static friction prevails, that means there is no relative motion of the two surfaces. That means if this has an acceleration of 1.5 meters per second squared, this also has an acceleration of 1.5 meters per second squared. If the acceleration of this is 1 meter per second squared, then frictional force again would be of even lower value. That will also fall in the static regime. Again, there will be no relative motion between the two surfaces. The acceleration of m1 will also be 1 meter per second squared. Yes or no? Right? Yes or no? Right? Which means, if I apply a force capital F, 1, the maximum common acceleration would be 2 meters per second squared. And that value of acceleration is reached when the frictional force between the two reaches its maximum value of 20 newtons. Yes or no? Right? Now, let's see, when does that happen? Let us find the value of F this is 20 kgs, this is 10 kgs. Let me find the value of F for which they have a common acceleration of 2 meters per second square. Let me find the value of F for which they have an acceleration of 2 meters per second square, which is their maximum common acceleration. Right? Okay. I can apply generalized Newton's second law to this system. Right? I consider the system m1 plus m2. When I look upon them as one unit, what's the nature of friction between, then the forces that they exert on each other will be deemed internal forces. Right? Then the only external horizontal force will be capital F. Friction that they exert on each other will be an internal force. Right? So then, let me apply Newton's second law to the system comprising m1 and m2. So what would F be? F would be 20 plus 10 into 2. Yes or no? Which is 60 newtons. Yes or no? Now when F becomes 60 newtons, they reach a maximum common acceleration of 2 meters per second squared. And when they reach a maximum common acceleration of 2 meters per second squared, what's the frictional force between the two? Maximum static of 20 newtons. Maximum static of 20 newtons. Right? Now, so very clearly, if capital F becomes 60 newtons, when I keep increasing capital F, when capital F grows from 0 to 60 newtons, 0 to 60 newtons, right? The common acceleration grows from 0 to a maximum of 2 meters per second squared. The common acceleration grows from 0 to 2 meters per second squared. Frictional force grows from 0 to 20 newtons, maximum static friction. Yes or no? So when F is 40 newtons, maximum common acceleration will be less than 2 meters per second squared. Frictional force will be less than 20 newtons. Yes or no? Say for example, say if somebody applies a force equal to 30 newtons, right? Then maximum common acceleration will be less than 2 meters per second squared. Frictional force will be less than 2 newtons. If the frictional force is less than 2 newtons, if the frictional force is less than 20 newtons, if the frictional force is less than 20 newtons, that means they will move with common acceleration. Yes or no? So values of capital F less than 60 newtons will cause the two bodies to move together, will cause the two bodies to move together, right? So when F is 30 newtons, then what happens to the common acceleration? What happens to the common acceleration when capital F is 30 newtons, say, when capital F is 30 newtons? They will move together, right? They will move together. What happens to the common acceleration? F would be 30 divided by 30. Yes or no? 30 newtons divided by total mass, which is 30, which is 1 meter per second squared is the common acceleration between the two surfaces. Yes or no? Do you all understand this? Huh? And at this juncture, yeah, if I want to compute the frictional force between the two surfaces. Now, when I have to look at the frictional force alone, it would be good to look at the lower body, because the lower body is being driven by friction alone. Lower body is being driven by friction alone. So let me look at the free body diagram of the lower body at this juncture for this condition, F equal to 30 newtons, which results in a common acceleration of 1 meter per second squared. Right? Are you there with me? Sure, everything. So let me look at the free body diagram for this situation of the lower block. Lower block is this, which is 10 kgs. And what drives the lower block? Friction. Friction. 20 kg block communicates to the 10 kg block of frictional force to the right, so that they could move together with a common acceleration. And in this case, they are moving together, so this frictional force has to be static in character. Okay. And to cause it to have an acceleration of 1 meter per second squared, what would be the value of F? 10 into 1. They have a common acceleration of 1 meter per second squared. Now I look at the lower body alone. Just because I am looking at the lower body alone doesn't mean it will have a different acceleration. Its acceleration will still be 1 meter per second squared. But it is important to understand what causes the lower block to accelerate. It's the frictional force that the upper block exerts on the lower block that causes the lower block to accelerate. So how much should friction be so that the lower block has the same acceleration of 1 meter per second squared as the upper block? Friction should be mass into acceleration. So which is like 10 into 1, 10 newtons. We expected that to be less than 20 newtons because static conditions were prevalent. Static conditions were prevalent. Right? If I look at this juncture, the free body diagram of the upper block. Look at the upper block. At this juncture, for this force, the upper block would be, this is 20 kgs, this is 30 newtons. If M1 exerts on M2 a frictional force like this, M2 will exert on M1 an equal and opposite frictional force like this. Now, On the 10 kg block, the frictional force is 10 newtons to the right. So what would be the magnitude and direction of frictional force on the 20 kg block? 10 newtons to the left. What is the net force acting on it? 20 newtons divided by 20 kgs. That gives me 1 meter per second squared as the acceleration. So consistent. Consistent. This exhibits consistency. Yes or no? So when I increase F from 60 newtons, their common acceleration grows from 0 to 2 meters per second squared. Frictional force grows from 0 to a maximum value, and they move together up to 60 newtons. Up to a value of 60 newtons of the externally applied force on the upper block. They are capable of moving together because friction can give enough juice for the lower block to be driven in sync with the upper block. Right? But now, if F becomes greater than 60 newtons, up to 60 newtons, they are moving together because there is ample friction to support common acceleration. There is ample friction to support common acceleration. Yes or no? Right? But if F becomes more than 60 newtons, now at 60 newtons, friction becomes a maximum of 20 newtons, right? But this is M1 equal to 20 kgs, M2 equal to 10 kgs. When this becomes, say, F equal to 60.5 newtons. That means it's trying to give an acceleration of more than 2 meters per second squared to the upper block. That means now the lower block requires friction greater than 20 newtons to have a greater acceleration. But that is not possible. So friction on the lower block continues to be 20 newtons after this. Right? I'm assuming that maximum static friction is approximately the same as kinetic friction. After F equal to 60 newtons, relative motion starts between the two surfaces. The two surfaces are on tenterhooks. They are on the verge of sliding over each other after F equal to 60 newtons. Right? For 60.5 newtons, therefore relative motion commences. Relative motion starts after 60 newtons. So now this is so frictional force that exists between the two surfaces is kinetic friction, which I will assume is approximately equal to maximum static friction. At F equal to 60 newtons, friction assumes its maximum value equal to 20 newtons. So then after F equal to 60 newtons, it remains at 20 newtons. I'm assuming that kinetic friction is approximately the same as maximum static friction. So then the friction on the lower block after this point, no matter what this externally applied force is, friction remains 20 newtons. Friction remains 20 newtons, its maximum possible value. Even if this becomes 5 lakh newtons, this will remain 20 newtons. If this becomes 10 lakh newtons, this will still remain 20 newtons. And this is my 10 kg block. That means no matter what my capital F is after 60 newtons, this will remain 20 newtons, and the acceleration of this will remain constant at 2 meters per second squared. It will not vary after this. Right? But if you look at the upper block, which is the 20 kg block, there is 60.5 newtons. And it applies on the lower block a 20 Newton force like this. So the upper block will experience a 20 Newton force like this, which is kinetic friction, but approximately equal to maximum static. What would be the acceleration of the upper block? AU, the acceleration of the upper block would be 60.5 minus 20 divided by 20, which is 40.5 divided by 20 meters per second squared. 2.0025 would be the acceleration of the upper block. And it will go on increasing. When I go from 60.5 to 70, it will be more. But this will remain the same because it has reached its upper limit. This becomes 100 newtons. Acceleration of the upper block can grow indefinitely. but the acceleration of the lower block will be limited, Yes or no? So, from capital F equal to 0 to 60 newtons, it's all good story for the couple. They move together in harmony, right? Their common acceleration grows from 0 to a maximum value of 2 meters per second squared. Friction grows from 0 to 20 newtons. Everything proportional and in place. Disruption starts when capital F exceeds 60 newtons. Relative motion commences. But the lower block then continues to move with 2 meters per second squared, not taking cognizance of the externally applied force. The externally applied force in its own right will have an ever increasing acceleration based on the externally applied force. But the frictional force between the two surfaces will then be preserved at 20 newtons thereafter. Yes or no? This is the story. This one illustration should send home a lot of signals, a lot of important signals, a lot of key ideas and notions related to friction. And I am assuming you are in sync with me. You have understood everything that I have communicated, right?